Welcome to our discussion on dynamic panel data model, and today what we will do, since we have already completed all the discussions about the theory and I have also demonstrated using the statistical software how to estimate a dynamic panel data model and different issues involved while you estimate. In today's class, I will just summarize from the beginning so that you will be able to know what are the key elements that you should keep in mind while estimating a dynamic panel data model, right. So, this is a summary of entire discussion that we had in dynamic panel data model. So, this is dynamic panel data model that we are going to discuss. So, our model looks like YIT equals to rho yi t minus 1 plus beta xit plus uit, where uit is actually summation of the unobserved individual specific effect plus the idiosyncratic error. Firstly, we need to keep in mind before applying dynamic panel data model, we need to first justify theoretically why do you think that you need a dynamic panel data model in your context. So, your situation should be of partial adjustment type. That means, for any changes in your explanatory variable xit, YIT should not be able to adjust itself in the same period. If it does, then it would be a case of instantaneous adjustment. When it fails to adjust in the same period, then only we call it a partial adjustment model, and that partial adjustment model, the other name of it is dynamic panel data, because by partially adjusting, dynamism is introduced in the model. So, a simple transformation that we have discussed is, if we subtract yit minus 1 from both the sides of this equation 1, then what we will get? Yit minus yit minus 1 equals to rho into 1 minus rho into yit minus 1 plus beta xit plus uit. So, this is the model, and by partial adjustment what we mean that this rho should be less than 1, right. Rho should be less than 1, and that means if rho is less than 1, then only we get a partial adjustment model. Rho equals to 1 means this term will be 0, that means the lag dependent variable will disappear from the model, and that will imply an instantaneous adjustment. Adjustment model, which is basically the static panel data model, and rho greater than 1 is unstable. So, this is the situation of partial adjustment. There might be many reasons for getting partial adjustment or dynamic panel data model. We have discussed only one case wherein we were discussing merely the employment data, right. Employment of a firm or employment by any sector, that depends on what is the employment you are already having, because what we discussed is the hiring of new employer and firing the existing one is costly. That is why employment depends on your previous year employment. YIT is a function of YIT minus 1. There might be other cases, right? So, if you want to model, let us say, a firm's output, even that is also kind of dynamic in nature, because your Tth period output may depend on previous periods output, how much you have already produced, how much you could sell, and how much was there in your inventory, right. There might be many cases for that. So, we need to carefully justify our need for a dynamic panel data model. Otherwise, when we just because we have some data and we know the code about how to estimate in the statistical software, we should not use when it is not required, right. We need to carefully understand the situation and justify. Now, in case we have a dynamic panel data model, then what happens here, that the main feature of this model, I am writing this model once again, YIT equals to rho YI t minus 1 plus beta XIT plus AI plus VIT. I am writing in this form. Since YIT is a function of AI and there is no t subscript over here, what we discussed, that YIT minus 1 is also correlated with AI. That means it leads to endogeneity, because AI and VIT constitute the composite error term. So, there is endogeneity in this model and OLS is not applicable. Then when OLS is not applicable, if we do still estimate the model using OLS, basically we will end up with having a dynamic panel bias, and we discussed that OLS actually leads to, in this situation when you have dynamic panel data model, if you apply OLS, that will lead to overestimation. Overestimation of rho hat. To remove this AI, if we apply the fixed effect transformation like what we used to do in the context of static panel data model, then what we discussed, that a fixed effect model will lead to underestimation of rho hat. So, that means OLS will give you an upper bound and FE will also give a lower bound of rho hat. Is it clear? Right? OLS is giving upper bound because the we are ignoring that there is dynamism in the system, and what is happening here, that a positive correlation between this YIT minus 1 and AI, and we have also given an example why YIT minus 1 and YI is positively correlated, because you can understand, you can take a situation where the firm is experiencing a negative employment shock, then in the next period both AI, the unobserved effect, and YIT minus 1 would be lower than what was happening earlier. So, in all the consecutive periods, rather your YIT in your AI and YIT minus 1 would be lower, and as a result of which they will have a positive correlation that we have already discussed. And in fixed effect transformation, it will have a negative bias, because the transformation, when you make YIT minus YI bar, then you will get VIT minus VI bar. A negative sign before that VI bar will lead to negative correlation between YIT minus 1 and your VIT, and as a result of which fixed effect transformation will give you underestimation of rho hat. and these two will give you the upper and lower bound of your estimate. So, true estimate must lie, true estimate of rho hat then should be greater than your fixed effect, but it should be greater than fixed effect, but less than your OLS. So, this is something whenever we are applying and estimating a dynamic panel data model, we need to first check the upper and lower limit of your estimates, and then applying dynamic panel data model estimation technique. When you get a rho hat, then you will see whether your rho hat is actually lying within the interval of FE and OLS, right. Then we have also discussed that when neither OLS nor FE is applicable, the other transformation is first difference. So, FD transformation we can apply, and that will make it YIT minus YIT minus 1 equals to rho into YIT minus 1 minus YIT minus 2 equals to beta XIT minus XIT minus 1 plus VIT minus VIT minus 1, right. So, here what is happening, even after first difference also we can see that YIT minus 1 is here and VIT minus 1 is here. So, that is why YIT minus 1, that means this variable delta YIT minus 1 is actually correlated with delta VIT, and as a result of which we are again ending up with endogeneity. So, even fixed first difference transformation also cannot rule out the possibility of endogeneity, because this is correlated, right. So, what is the solution then we offered? We said that when FD is not workable because of this endogeneity, we will use IV either delta YI T minus 2 or delta YI T minus 2. These are the two instruments we can use, right. And the method, we said that this is the suggestion given by Anderson and Hsieh. He said we should take the first difference. So, that means this is the suggestion given by Anderson and Hsieh. We should take the first difference and then use the instruments. Now, one thing we should mention over here about the autocorrelation problem. In this model, when we are writing YIT equals to rho YIT minus 1 plus beta XIT plus AI plus VIT, what we are saying that YIT minus 1 is correlated with AI, and what we can write that YIT minus 1 is actually, so I can write YIT is a function of YIT minus 1. Now, the way I have written the equation, I can write the same equation for YIT minus 1, and in that equation the error term would be VIT minus 1. So, that means yit minus 1 is a function of vit minus 1. So, that means from this what I can write then yit is also a function of vit minus 1. Yit is already a function of vit, right. So, that means vit is correlated with yit, yit is correlated with vit minus 1, then ultimately vit is a function of vit minus 1. So, that means the presence of lag dependent variable is leading to autocorrelation, and that autocorrelation is of order 1. So, the structure of the model itself gives AR1, but if we assume that VIT are serially unrelated, uncorrelated, then AR2 and higher, let us say ARP, should not be there. Right. Now, what will happen actually if AR2 is there? What happens when what happens? So, if we look at what is the instrument we are using YIT minus 2, assuming that YIT minus 2 would be correlated with delta YIT minus 1, but they will not be correlated with VIT minus delta VIT. But in case there is higher order autocorrelation, that means VIT is also correlated with, in presence of AR2, VIT is a function of VI t minus 2 also, second order correlation is also there. That means earlier what we were assuming that this YIT minus 2 will not be correlated with this transform error term, that will no longer valid, because VIT itself is correlated with VIT minus 1, and that means obviously YIT minus 2 is a function of VIT minus 2. So, that means I am saying that YIT minus 2 is also a function of actually VIT. So, YIT minus 2 can no longer be an instrument if there exists second or higher order autocorrelation. That is why when we estimate the dynamic panel data model, we must check whether AR1 is there and whether AR2 is not there. AR1 must be there because of the construction of the model. If AR1 is not there, that means equivalently we are saying that there is actually no need of estimating a dynamic panel data model. Okay, because there is no importance of YIT minus 1. That is why by construction AR1 must be there, but AR2 should not be there. If AR2 is there, that means as if we are saying in presence of, we should write it down, in presence of AR2, neither yi t minus 2 nor delta yi t minus 2 are valid instrument. Okay, that is one thing we need to keep in mind. Then another important point, we talked about dynamic panel bias and we also talked about nickel bias. That means application of Fe and Fd transformation, how that leads to nickel bias. Because both, in case of both Fe transformation and Fd transformation, we saw that we could not rule out the possibility of endogeneity, and this nickel bias is of order 1 by T. So, that means as T tends to infinity, this bias tends to 0. That is why whenever we will be estimating dynamic panel data model or DPD, DPD should be applied in context where T is small and in, that means the number of observations in the panel is large, right. That is also one thing we have to keep in mind. If T becomes large, then the bias will automatically get vanished. We do not have to estimate the model using this complicated dynamic panel data estimation technique. So, that is one thing we have to keep in mind, that this is a situation wherein my T is actually small, N is large, that means we are talking about a micro panel. Right. So, we will, when there is this type of problem, T is small, N is large and we have lag dependent variable in the right hand side, and then we are assuming that there is no AR2, we can go ahead with this estimation suggested by Anderson and Hsieh, wherein we will transform the model, we will take the first difference and we will use yit minus 2 or delta yit minus 2 as instrument. So, what was happening in case of Anderson and Hsieh's model? So, Anderson and Hsieh's main problem was that in their model, since they said only yi2, only yi t minus 2 as IV. So, this implies not all available moment conditions are utilized. Therefore, we can increase the efficiency of rho hat to a larger extent following this Holzhausen Holdziakin's technique. What they say, that we will use YIT minus 2 as instrument for all the periods and replace the missing observations by 0, because in Anderson and Hessio's approach, the moment we use other lags also as instrument, then we saw then your sample length was going down. Okay? So, there was a trade off between lag length and sample length that we discussed. So, following Anderson and Hessio's approach, the more lag you include, the more observations we are going to lose. Then Holdziakin et al., they came up and say that we can actually use one single instrument YIT minus 2 for all the periods, YIT minus 2 for all, okay, for all the period, and replace the missing observations by 0. That was Holdziakin et al.'s suggestion. But then again, the original idea is to use more moment conditions. Whatever lags are available, we need to use all of them to increase efficiency of rho hat. That is the reason next model is the most popular one, came up by Arellano and Bond 1991. So, what they say, that use YIT minus 2 as well as all other lags, as and when available. That is what Arellano and Bond said, right. So, for example, in third period, what will happen? You will have only YIT minus 2, that means YI1 is available. But when we go to fourth period, then we will have YIT minus 2, that means YI2 as well as YI1, because YIT minus 2 and YIT minus 3 is also available. When you go to fifth period, then YIT minus 2, YIT minus 3, YIT minus 4, all these 3 are available. So, as we move on to the higher periods, we will get more and more lags, and we will include whatever is available, and missing observations, as Holdziakin et al. Suggested, we will replace by 0. In that way, Arellano and Bond, they increase the efficiency of their estimates.